Hey everyone, Mr. Hedrick back here to talk about a new topic today, and that's going to be building polynomials, which is actually the opposite of what we have been doing so far, which is breaking down polynomials by, for example, factoring and then solving by factoring. So just to reiterate what we've done in the past, we've taken a polynomial function, broken it down by factoring, so something times something equals something else, right? These two parentheses multiply back to give your polynomial. To break them down, we think about what times what equals x squared, and we know that x times x is x squared. What times what is negative 12, but also adds to give positive 4. So 6 times negative 2 is negative 12. 6 minus 2 is 4. This is how we've factored in the past. We've also used the box method. And then solving, or finding roots or zeros of a polynomial, is to think about what would turn everything here into 0? What numbers would x have to be? And so we would, for example, set x plus 6 equal to 0 and solve. We would set x minus 2 equal to 0 and solve. And we would find that there are two solutions to this degree 2 polynomial, right? Two roots or two zeros, two numbers, in other words, that you could plug in and turn everything here into a 0. And we've seen this on the graph as well. These would be your x-intercepts, negative 6 comma 0, 2 comma 0. This is how we've solved by factoring in the past. Today, we're going to work in reverse, meaning if I give you roots or zeros or solutions, you should be able to work backwards from what you've done so far and build back up that polynomial function where these roots, zeros, or solutions came from. So for example, if I take those same roots and zeros and I ask you to build a polynomial of least degree, meaning don't have any excessive solutions or roots or zeros, don't include something like, oh, well, I want to say that x equals positive 7 is another solution here. No, don't do that. Okay. Only work with what you're given unless you have a special case, and we'll get to those in a second. But build a polynomial of least degree with a lead coefficient of 1. So again, no unnecessary items included when you're actually building up the polynomial. And then let's say that we have that x equals negative 6 and x equals positive 2. How do we build a polynomial function from these roots, zeros, or solutions? What you're going to want to do is to take those numbers and think about where did they come from. They must have come from x plus 6 and x minus 2. Why? Because if we found those numbers, right, that came from setting x plus 6 equal to 0, subtracting 6 to both sides, and getting x equals negative 6. Also, x minus 2, we must have set that equal to 0, and added 2 to both sides and get x equals positive 2 as a solution. So in other words, whenever you're building a polynomial, you're going to take your roots, zeros, or solutions and plug them into parentheses with opposite signs, usually. Okay. Then we would want to multiply this out, so we would use the box method, right? We would take x times x and get x squared. We would take negative 2 times x and get negative 2x. X times positive 6 in this case is 6x, and 6 times negative 2 is negative 12. This would help us to build the function that these solutions came from, or at least one function that these would have come from. And in this case, x squared, combine like terms, plus 4x minus 12. This is the polynomial with the smallest or least degree and a lead coefficient of 1, as we can see here, where these solutions can be found from. Okay. Again, it's just working in reverse from what you've done so far. Factoring and multiplying are opposites. We've worked with factoring. Now we're working with multiplying yet again, seeing how what we've talked about in the past, which is how to multiply polynomials, can be useful in this sort of context where we're building polynomials given certain context to our graphs or functions, those being the roots. Now, there are some special cases to think about. Okay? Those special cases are as follows. If you're ever given a solution or root or zero with a positive I or a negative I, those solutions must always come in pairs, conjugate pairs. So if I give you x equals positive I as a solution, you should know that x must also equal negative I, right? They go together. You can never have just one complex solution. There's always two. Same thing, by the way, with square roots. If I give you x equals a square root of 5, you should know that x equals negative square root of 5 is another solution, or vice versa. If I give you x equals negative square root of 5 as a solution, root or 0, x equals positive square root of 5 must be as well. Again, conjugate pairs always go together. I's with negative i's, square roots with negative square roots. And lastly, if we have a problem where we are given a root 0 solution and x equals 0, it's a bit special. Instead of plugging a number into parentheses, I mean, you could do x plus 0 or x minus 0, but that doesn't really change anything, right? Adding by 0 never changes anything. Really, when you have x equals 0, that comes from having, let's just make up an example real quick. That would come from multiplying x in front, right? X plus 0, x minus 0 doesn't really change anything. In this case, x equals 0 came from an x that you multiply everything else in your polynomial by when you're building it back up. So, an example of this would be, what if I gave you a problem where I'm asking you to build, that involves two special cases, right? In this case, we have x equals 0 and x equals square root of 6. Well, that must mean that x also equals negative square root of 6. So you should be able to tell me that. If I only give you one, you should be able to give me the other. Now, again, this means that when we're building a polynomial, we're going to multiply everything by x at the very end. This means that we have x minus the square root of 6. This means we have x plus the square root of 6. We have those conjugate pairs together. We would use the box method to multiply this out, right? Always multiply your conjugate pairs first, by the way. Okay, so x times x would be x squared. X times negative square root of 6 is negative x squared root of 6, which looks odd, but that's okay because we get positive x square root of 6 here as well. These cancel. And it always happens with conjugate pairs. That's why it's not that difficult to work with them. Okay? Multiply these out first. And then a positive times a negative will be a negative. We have a square root, and 6 times 6 is 36. That gives us, we know what the square root of 36 is, x squared minus 6. Right? Square root of 36 is 6. But don't forget, we still have not multiplied with x yet, right? We multiplied these parentheses, but we haven't yet multiplied by that x. In other words, take x, multiply it out. You should get a polynomial of least degree with lead coefficient of 1, which is x cubed, right? X times x squared, 1 plus 2 is 3. X times negative 6 is negative 6x. And here we have it. The polynomial where if you graph this, you'll find that the graph crosses the x-axis where? When x equals 0, when x equals the square root of 6, and when x equals negative square root of 6. You can check that on your own using desmos.com/graphing, as we've talked about in the past. Those are your special cases. Conjugate pairs go together, i's with i's, square roots with square roots, and x equals 0 means multiply x in front of any other parentheses that you might have in your problem. One last thing I want to talk about to end this video will be what's called multiplicity. And multiplicity is the idea that sometimes you have what are called repeated solutions, roots, or zeros. So, what do I mean by that? Well, let's say that, for example, this was a problem that we wanted to build, right? We have roots of negative 2i, 7, and 4 with a multiplicity of 3. Now, if we wanted to build this up, we would build it by multiplying, and what that might look like to start is we would know if that's one of our roots, zeros or solutions, then this one has to be the other, right? Negative 2i, positive 2i, those are your pairs. I's have to go together. So you'll have x plus 2i times x minus 2i. That will be part of your way to build up your problem. And you have x equals 7, so that means that that must have come from x minus 7. Okay. That'd be another way that you'd start to build this up. And if you have x equals 4, but the multiplicity of that is 3, that means, again, you're going to take that x equals 4, plug it into parentheses with the opposite sign, but this is a repeated solution, meaning we should have 3 of these parentheses, or in other words, an exponent of 3. Okay. 3 different solutions there, right? X minus 4 times itself 3 different times. That's what multiplicity means. Now, I'm not going to multiply this out. You could do that yourself. It would take a while. But what I did want to show is what multiplicity is, because when we start talking about that next week in relation to graphs, that's actually going to help determine what the shape of a graph looks like. So it's not always going to be that the graphs that you're going to see cross straight through the x-axis, as you've seen in the past. Sometimes you have a vertex, or sometimes you have what's going to be looking like a little squiggly line. If you graph this as it's exactly laid out, where x equals 4, you'd have a different shape or behavior of that x-intercept, where that graph looks a little bit different